These are the notes for 7.1 and 7.2, where we talk about rational functions and also multiplying and dividing rational expressions. So we'll start out with a definition. A rational function is just a function whose rule or whose pattern is a ratio of two polynomials. So you can think about a rational number is a ratio of two integers. So you want to think about it as like a fraction or a fraction involving polynomials. So the numerator is a polynomial and then the denominator is a polynomial. And one of the things we always like to know about functions would be what the domain of the function is. So if we've got ratios of polynomials like this, what we want to know is what's the general pattern for when such an expression will be undefined. And if you recall, fractions are undefined when the denominator is 0. So a rational expression will be undefined whenever the denominator is 0. So how do you find the domain of a rational function? Well, you'd set the denominator to 0. And exclude the values of x that make the denominator 0. So then we're asked to find the domain of each of the example polynomial functions, rational functions that are given. So for the first one, we would just look at the denominator, and we'd say the denominator is x minus 2. So the domain we could write as the set of all x such that x is not 2. Because if we have 2 as our x value, the denominator of this expression will be 0, so the function will be undefined. And for g, the only thing in the denominator is x, so we would just say the domain of this function would be the set of all x such that x isn't 0. Right? Anything else is fine, but if x is 0, we have a problem. Keep in mind the numerator can be 0, that's not a problem. If the numerator is 0, fine, but if the denominator is 0, that would be undefined. On function h, the denominator is 2, so no matter what x is, that denominator is not going to be 0 because it's always 2. So the domain for h is all real numbers, or you could write negative infinity to infinity, or you could just write out all real numbers. Any of those are fine. On j, we need to do a little bit more work because that denominator is more complicated. So if we want to know the domain, we would set that expression equal to 0. Oops, I lost an x. And we would factor this. So we'd have what, x plus 7 and x minus 1. Let me rewrite this, that's a mess. So we just set the denominator equal to 0, and in this case, since it's a polynomial, we would factor it, and we would say x shouldn't be negative 7 and x shouldn't be 1 for the domain. So we want the set of all x such that x is not negative 7 and x is not 1. Right, so to find the domain, you set the denominator equal to 0 and throw out those x values. The next thing we need to talk about is simplifying a rational expression. And it's just like simplifying a fraction. You try to factor everything and then create ones from the common factors. So in a here, if we factor the numerator and the denominator, so factor, remember, means to write as a product. So this already is a product. We could expand things a little bit, but let's just do this. If we group the factors that have common factors, so 12 and the 6, those are constants, that reduces to 2. X squared over x, that reduces to x. and y cubed over y reduces to y squared. Right, we're just using the rules for exponents that say if we have a fraction, we subtract the exponents. So 2 minus 1 on the x for the new exponent, and 3 minus 1 on the y for the new exponent. And that would be considered simplified. On B, the numerator is already written as a product. It's already 3 times x. The denominator has a sum. So what we'd want to do is factor out anything we can. We could take out a greatest common factor of 3. So we could write this as 3 times x and 3 times the group x plus, 2x plus 3. And then we can say, all right, I've got a matching factor of 3, so that makes 1, which I don't need to write. So my final answer would be x over 2x plus 3. Notice now there is an x in the numerator and there's an x in the denominator, but there's not a factor of x in the denominator. So I can't reduce these because this x is involved in a sum. On C, notice there's just one factor in the numerator, x minus 7, and one factor in the denominator, 7 minus x. There's no multiplication. And those are almost the same, but they're subtracted in the opposite order. So you can right away just reduce that to -1 if you remember that these are opposite factors, or if you prefer, you can factor out a -1 and make this x minus 7. And then you could reduce these, and you've got 1 over -1, which is -1. Anytime you have factors that involve subtraction in the opposite order with the same terms, those would reduce to -1. So you can show your work like this, or you can just cancel, reduce it to -1. All right, then on D, we've got a sum of cubes. So we just have to remember that pattern. A sum of cubes is always 2 factors. And remember, we used that matching opposite plus acronym for the signs. So x matching sign and 1 from the cube root of x cubed and the cube root of 1. And then use those pieces to build up the other factors. We want x squared and 1 squared on the ends with the opposite sign and then a plus and the product of x and 1 in the middle. And now that we've factored that, so we said this was the sum of cubes pattern. If you're not remembering that pattern, review the factoring part 2 video. So sum of cubes pattern, and the denominator happens to be the same as that second factor. So right away we can reduce. We don't need to factor this, and actually it's prime, so we couldn't factor it. And our final answer should just be x plus 1. Then on E, it looks like we could combine these like terms, or let's go ahead and just for the practice, factor by grouping. So if I factor by grouping, I would take out an x, and I'd have x minus 2, and then I would do plus 4, and I would also have x minus 2. That's not factored yet because of this plus, right? So we have to do always 2 steps in our factoring by grouping. That's going to finally factor as x plus 4x minus 2. And the denominator, we've got what? An x and a 2x plus 3 plus 4 times 2x plus 3. And again, this is not factored either because of this plus. So it's not okay to reduce anything yet. So we can't cross out these x's and these 4's. We have to go one step further and make sure we actually get it factored and then reduce things. Otherwise, you'll end up with the wrong answer. So finally, at this very last step, so grouping is always 2 factoring steps at least. Now we can say our answer should be x minus 2 over 2x plus 3. And you don't need the parentheses around the numerator and the denominator. Sometimes I put them there, sometimes I don't. But if there's only one factor, you can just leave it with or without parentheses. Then we need to talk about multiplication of rational expressions, and then on the next page we'll talk about division. Multiplication is very much like simplification. We're going to factor everything, factor all the numerators, factor all the denominators, and then reduce. So we don't actually multiply anything together before we simplify. We just factor, 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 and divide. So factor and reduce. Factor and basically reduce. So here, if I factor the first numerator, it's a trinomial, so I would want to do reverse FOIL. I'll need a 2x and an x. From the signs, I know we're going to have matching signs, both negative. And it looks like a 3 and a 3 will work, because that'll give me a plus 9 and a minus 3x minus 6x for a negative 9x overall. The second numerator is, we can break up as 2 times x. So keep in mind there are actually 2 separate factors there. And in the denominators, the best we can do is just to take out a greatest common factor in each of these. So greatest common factor of 4 in the first one times 2x minus 3. And in the second, we have a greatest common factor of x and a second factor of x minus 3. So this goes with these factors. This turns into these factors. That turns into these factors, and then the x squared minus 3x factors that way. So I'm trying to highlight the matching factors there for you. And then we start reducing. So we've got a 2x minus 3 in the numerator and the denominator. We've got an x minus 3 in both locations. We have an x in both locations. And then the 2 over 4 we can reduce to 1/2. So 1/2 for the final answer. Right, so the key is to factor, 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 and factor, and then look for matching factors in the numerator and denominator. All right, so numerator, we've got, let's try this, sum of cubes from the first one. So we've got x plus 2 times matching, and then we put the squares on the ends. X squared and 2 squared, opposite sign, and then a plus with the product of these in the middle. And then the x plus 3, there's nothing we can do to factor that, and so we'll just write it like that. And the first denominator looks like we would try to reverse FOIL, so we'd have x and opposite signs, so 1 plus, 1 minus. We want the product of -6 and the sum of -1, so -3 and +2 should work. And the last denominator, notice it matches one of the factors in the numerator, so we don't need to factor it, we're going to just reduce it. If we try to factor it, we'll find that it's prime. So put all the numerator factors in the numerator, all the denominator factors in the denominator. So you can put it over a single fraction bar, and then just match factors up. So this time we're left with x plus 3 over x minus 3. And it just seems like we should be able to reduce that, but we can't. They're not the same, and they're not opposite, because in the numerator and the denominator, the x's are both positive, so they have the same sign, but the 3's have opposite signs. So this is the best we can do. We just have to leave it like that. All right, a couple that are a little more interesting, where the exponents have variables also. So we saw in our factoring examples a few that were like this. When we have this pattern that looks almost like what we're used to in a trinomial, but has ends instead of just x squared and x, the factors will start with x to the n and x to the n. That'll give us an x to the 2n when we multiply these because we would add the exponents. And it'll also give us the right variable in the middle. So we just need to worry about getting this 4 and the 4 coefficient in the middle. So plus 2 and plus 2 should work. Then the other numerator, we can take out a greatest common factor of 2x. So I'll write that as 2 times x. And if we take out a 2x, we'll have, what, 4x minus 3. And this is nice because the denominator has a 4x minus 3, and it also has an x to the n plus 2. So we don't have to do any work down there. Those factors are just going to create 1s. And so our final answer will be 2x times x to the n plus 2. We can just leave that factored, that's fine. All right, similar example here next with y's instead of x's, but same idea. This is a difference of squares. This would be a perfect square because the numerator or the exponent is even. So if we factor that, we would have y to the 2n minus 4 and y to the 2n plus 4. And keep in mind now, this is not factored yet because it's another difference of squares. So let's just work on this factor alone. So we'd have actually y to the n minus 2 and y to the n plus 2 times y to the 2n plus 4. Right? So all of this stuff is just that one factor in the numerator. So after we have that factored, let's go back to the overall. So we'll have y to the n plus 2, y to the n minus 2 times y to the 2n plus 4. That's a sum of squares, so we can't factor it. Sums of squares are prime. 6 times y. And the denominator, we have factors that match factors from the numerator. Y to the 2n plus 4 times y to the n plus 2. So we can reduce. And our final answer should look like y to the 2n plus 4 times 6y. Oops, that's not true. Y to the n minus 2 times 6y. And you can write it as 6 times y or 6y, it doesn't matter, they're the same thing. Alright, so finally, division of rational expressions. This is just like multiplication, except you have to multiply by the reciprocal of the second fraction. So just like it is when you're dividing fractions, you multiply by the reciprocal of the second rational expression. So change two things. Flip the second thing over and switch the sign to multiplication. Okay. So your first step on this would be 36y over 7z squared. Change that division sign to multiplication and flip the second one over. Okay. And then you can just put it all together because it's all just multiplication. So 36 times y times 2 times z over 7 times z squared times 3 times x times y. So it's all factored, and we just want to reduce as much as we can. So the y's can reduce. There's no x in the numerator, so that x isn't going anywhere. One of these z's we can reduce, so we'll have a z in the denominator. 36 over 3 we could reduce to, what, 12? So we've got basically 12 times, let's do this, 12 times 2, so 24, over 7xz, looks like. So we have a z left in the denominator and an x. You could put the z and the x in any order, because it's multiplication and that's commutative, which means you can rearrange the order. No matching factors in the numerator and denominator, so we get to quit there. All right, so in B, if you want to just start factoring right away, you might as well. So we've got x, so this would be what, x minus 8 and x minus 4. We want to change this to multiplication and flip things over. So this x would have opposite signs, and we want a -5 sum and a -24 product. So -8 plus 3, right? So this ends up here. X squared minus 6x minus 16 will have x minus 8, x plus 2 would work. And then that numerator ends up in the second denominator, so x minus 4, x plus 3 should do it. So this ends up here. And then we can cancel matching factors, so x minus 4 from the numerator and 1 from the denominator, and x plus 3 from the numerator and 1 from the denominator, and an x minus 8 and an x minus 8. So keep in mind, once you've written it all as multiplication, it's like we have a big one single fraction bar all the way across, and we can reduce a matching factor from the numerator and from the denominator. So we end up with x minus 8 over x plus 2. And again, we can't cancel these x's or reduce these x's because those are not factors, those are terms. And similarly, we can't say, oh, 8 over 2, that reduces to 4, because this 8 is involved in subtraction and that 2 is involved in an addition. So no factors that can be further reduced there. Last example, again, with the variable exponents. We just want to factor. So we've got a trinomial. We would reverse FOIL. So I've got y to the n, 2 and 5 should work for the extra terms and then factors there. 10 we could write as 5 times 2 if we want to, or just leave it as 10. And then we multiply by the reciprocal. So this denominator is going to become our new numerator. We could take a 5 out of that. And that numerator becomes the denominator, and again that will be like a reverse FOIL, or you can even notice that it's a perfect square binomial. So you can either write this as y to the n plus 2 times y to the n plus 2, or just write y to the n plus 2 squared, same thing. And then look for factors to reduce it, and again remember then that this fraction bar just goes all the way across. We could reduce the 5s and one of these groups, but there would still be a y to the n plus 2 left in the denominator. And now notice we have two y to the n plus 5 factors, but they're both in the same location, so we can't do anything to reduce that. So we'll have to leave that, and we can write it as a square because there are two of them. And then in the denominator we have 2 times y to the n plus 2. And that would be our final answer. I believe that's the last example. Oops, there's an extra page of those notes. Sorry about that.